Hi, this is Mrs. Basin, and today we're going to talk about section 3.5, which deals with empirical formulas. So when you calculate an empirical formula, you have to be given the mass percent of elements. So you would have to have some information from some kind of experiment or results of some analysis of a sample that tells you which elements are present in the sample and then the mass percent. They might be given as percents, they might be given as grams, sometimes they might even give you the different elements as moles. So when you start these problems, you have to first pay attention to how are these being given. If they're given as mass percent, we assume 100 grams of the sample. So when you assume 100 grams, you just take the percent sign and change it to a gram sign. Then if we follow along this little path here, and this is just kind of an overview of how this is set up. But here's our first step here. So we're either given the mass or the grams. If we're given the mass percent, we assume 100 grams. Then we go from grams to moles. Okay, so this step here is grams to moles using the molar mass. And then from the moles, you're going to look for the lowest whole number ratio. So we're calculating the mole ratio, and that's what gives us the empirical formula. So the easiest way to look at these is to actually go through and do some example problems. So here's our first one. It says we have ascorbic acid, which is what's found in vitamin C. This contains 40.92% carbon, 4.58% hydrogen, 54.5% oxygen by mass. What is the empirical formula? So what we're going to do is first thing is list all the elements in that sample. So we have carbon, hydrogen, and oxygen. Now since they gave it to us as a percent, we're going to assume a 100 gram sample. So instead of writing 40.92%, I'm going to write that as grams. Hydrogen, I have 4.58 grams of that, and then I have 54.50 grams of oxygen. So before, on our little pathway that we just looked at, our first step is to convert to moles. So I'm in grams, so I'm going to take it to moles. So 1 mole of carbon is 12.01 grams. And these numbers are just coming right off the periodic table. So this would give me 3.407 moles of carbon in that sample. Hydrogen, 1 mole is equal to 1.01 gram, and that gives me 4.535 moles of hydrogen. Oxygen, 1 mole, 16, and again those numbers on the bottom are coming from the periodic table. That gives me 3.406 moles of oxygen. Okay, so now I'm in moles, so then I have one more step here. I have to look for the lowest whole number ratio. So to do that, what I'm going to do is divide all of these by the smallest number. So in my list that I have here, my smallest number is a 3.406. So I'm going to divide all of these, 3.406 divided by 3.406. And again, the reason I'm doing this is because I want the lowest whole number ratio. So that gives me a 1 down at the bottom here. This next one up gives me a 1.33, and this one gives me a 1. Okay, so at this point, now you're going to look at that ratio that you have. So I have a 1 to 1.33 to 1 ratio. Now these have to be whole numbers. So at this point, if these don't round, so if it's not a 0.1, so a number 0.1 or a number 0.9, then you have to multiply by some number so that they're all whole numbers. So then this last step here, we're going to multiply all of these by 3, because we know if we multiply 1.33 by 3, we'll get a whole number, which is 4. But whatever I do to one, I have to do to the others. So I'm going to multiply all of them by 3. And then these final numbers in the boxes are my subscripts. So my final thing to do here is to write out my empirical formula. So C3, that came from here, H4 came from there, O3, that came from down here. So this formula here, that's my empirical formula of ascorbic acid. Okay, here's another example if you want to try one more. If not, go ahead and skip ahead. Okay, I'm going to try to use the same colors here if I can remember what I did in the last one. All right, so this one is already given in grams, so I don't have to worry about that converting percent to grams, which is not that big a deal, but that kind of saves me one little thought process step there. So I know I have carbon, hydrogen, and oxygen again. They're not all going to be carbon, hydrogen, and oxygen, but these particular examples just happen to have that. So I have, now this is my total, so when they give you a big list of numbers, be careful which numbers you're pulling from the problem and make sure they're the correct ones. So this one says 3.758 grams of carbon, 0.316 hydrogen, 0.125 oxygen. So I don't need, right now I don't need this number up here. They're just giving me the total and then they're breaking it down into the individual components. So 3.758 grams, hydrogen 0.316 grams, oxygen 1.251 grams. All right, so step 2, I'm in grams, I'm going to change it to moles. So 1 mole, 12.01 grams, again from the periodic table. That gives me 0.3129. Hydrogen, 1 mole, 1.01 grams. That gives me, and these are moles again, I'll label them so we can keep track of what's going on here, 0.3129 moles as well. And then my last one, 1 mole, 16 grams for oxygen, and I end up with 0.07819 moles. Okay, so that's my mole ratio, but I want the lowest whole number ratio. So this is where I'm going to divide by the smallest. So this number down here is my smallest one. That'll give me a nice whole number there. If I divide these, 0.7819, that gives me 4. This one, 0.07819, that also gives me 4. So this time, these are already whole numbers, so I don't have to multiply by anything because these all came out to be the whole number 0.00 something, which is okay to round. So again, just like before, those are my subscripts. So this empirical formula is C4H4O. So that's my empirical formula of methyl benzoate. Okay, so that was how you calculate the empirical formula. Now the empirical formula, if you remember from before, is the lowest whole number ratio. But a lot of times the empirical formula for a molecule is not the same as the molecular formula. The molecular formula is the actual number of atoms of each element in that particular compound. So sometimes we need to convert from the empirical back to the molecular. So to do this, we would have to have either the molecular weight or the formula weight, which is basically the same, or you're looking at the ratio of the molecular weight to the formula weight. Now these can be a little tricky because sometimes those two things are used interchangeably, but the molecular weight is the actual, you can think of this as the actual weight of the compound. The formula weight is what comes from the empirical formula. Okay, so when we look at the ratio, what that tells us is what we're going to multiply all those subscripts in the empirical formula by to get to our molecular formula. So an easy little formula you can use here is N equals the molecular weight over the formula weight. Now if you forget which one goes where, the bigger number is always going to go on top. So the molecular weight is always going to be larger. So this larger number goes on top. So if you can't remember the difference between molecular and formula, whichever of those two numbers is bigger, that's the one that goes on top. Okay, so let's look at an example for this one. So this one is Mesitylene. This has an empirical formula of C3H4. So you've already gone through that other process and you've ended up with C3H4. So I have C3H4. Then it tells me my molecular weight, and that has to be given or experimentally determined, is 121 AMUs, which are atomic mass units. So I want to know what is the actual or the molecular formula of mesitylene. So to do this, I have to figure out what is this number that I'm going to multiply all of these subscripts in the empirical formula by to get to my molecular formula. So to do that, remember from the previous slide, we said N equals the molecular weight, which we said is always going to be either bigger or the same, over the formula weight. So the molecular weight they gave me, 121 AMUs. Now to get the formula weight, we're going to add up all the elements in that particular compound. So for this one, we're going to take 3 carbons plus 4 hydrogens. So when we do that, 3 carbons at 12.01 each plus 4, this is kind of messy here, 4 times 1.01. So all I'm doing is just adding up the empirical formula's weight. That gives me 40.04. Okay, so molecular weight, again, that was given in the problem, so that came from there. Formula weight, I had to go back to my empirical formula and add those masses up. So when I do that, I get a 3, and that is my N value on the outside. So now, and I'm going to move up here, I have C3H4, and like I said, my N value is 3. So now what I'm going to do is multiply each of those by that 3 to get to my molecular formula. So my molecular formula would be C9H12. Okay? Now, a bigger version of this is to not be given the empirical formula. So you have to do the empirical formula first, then you have to take that and figure out the molecular formula. So if you know what you're doing here and you're good with this, go ahead and skip ahead. If not, we're going to do one more empirical formula example, and then we're going to tag on that molecular formula stuff at the very end of this problem. Okay, so we're going to start with our list. So I have carbon, hydrogen, oxygen, 38.7 grams of carbon. It's a percent, so I'm changing it to grams. 9.7 grams of hydrogen, 51.6 grams of oxygen. Okay, then I'm going to, I forgot to change color. All right, then I'm going to take those, convert them to moles using my molar mass. So that gives me 3.222 moles. 1 mole, 1.01. That gives me 9.604 moles. Last one, 16 grams, 3.222 moles. Okay, next up, divide by the smallest so I can get that lowest whole number ratio. Divide all these, 3.222. Okay, so that's 1, 3, 1. Those are nice whole numbers. I don't have to multiply anything. So those are my empirical formula subscripts. So my empirical formula for this is CH3O. Okay, so what I need to figure out now then is if that's my empirical formula, what is my molecular formula? So to get to molecular, I have to figure out N. So again, N is molecular weight divided by formula weight. Okay, now what is given up here, it says it's molar mass. So this is where that molecular weight thing gets kind of tricky. So molecular weight could be used interchangeably with molar mass. So that's the mass of the compound. So that molecular weight is 62.1. I'm going to divide that by my empirical formula weight. So I have 12.01, and I'm going to do this kind of simplified here, plus 3 times 1, which is 3, plus 16. So I'm just adding up the masses of all this. Okay, so this then, 62 divided by 31, gives me a 2. So my N value equals 2. So now I'm going to multiply my empirical formula by 2. So I end up with C2H6O2. And that's my molecular formula. Okay, the last concept in this section is something called combustion analysis. So this is a different way to figure out or analyze a sample. So in a combustion analysis, something that contains carbon, hydrogen, and oxygen, a hydrocarbon, is analyzed through combustion. So there's a little chamber there. O2 is pumped in and is basically combusted. When the sample comes out, there is an absorber for water that's produced, and there's an absorber for the CO2 that's produced. So this is your little basic combustion reaction here with H2O and CO2 produced. Then what you're doing is, if you know how much water is produced, you can use that to figure out the hydrogen. If you know how much CO2 is produced, you can use that to figure out the carbon. Then you can subtract those two amounts from the original amount to get the oxygen, which is your third component. Okay, so again, this is one of those things that's probably simpler just to go through step by step. So here's an example. We want to know how many, if we have a sample of isopropyl alcohol, and we know that the isopropyl alcohol has carbon, hydrogen, and oxygen. So just like before, we have to know what the original elements are. It's analyzed by combustion, and this is my original amount that was combusted. Go back to my other color here. All right, so my total sample was 0.255 grams. Okay, so in this particular problem, that is going to be important. It tells me that it produces this much CO2. So CO2 that was produced was 0.561 grams. And then the H2O that was produced was 0.306 grams. Okay, so I don't have nice, neat carbon, hydrogen, oxygen amounts like I did in those other problems. So to do this, it's going to be a little more complex. So what I have to do first is I'm going to use my CO2 to get carbon. Then I'm going to use my H2O to get hydrogen. Now the reason I can't use either one of those to get oxygen is because oxygen is in both of them. Okay, so I'm going to start with my CO2, and like I said, I'm going to use that to get carbon. So I have 0.561 grams of CO2. So first step here is to convert that to moles of CO2. So 1 mole of CO2 is 44.01 grams of CO2. Then once I'm in moles of CO2, now I can get to moles of carbon using the ratio within that formula. So for every 1 mole of CO2, I have 1 mole of carbon. So there's 1 carbon for every 1 CO2. Now I can go to grams of carbon using the molar mass of carbon. Okay, so I started with grams of CO2, went to moles of CO2, used that to get to moles of just carbon, then went to grams of carbon. So when I do all of that, I end up with 0.153 grams of carbon. Okay, now I'm going to use the water to get to hydrogen. So I have 0.306 grams of H2O. Same process here, but this time I'm going to H. So I'm going to go to moles of H2O, molar mass of water, 18.02. Then I'm going to say in 1 mole of water, there are 2 moles of H's. So I'm looking within that compound, H2O, for every 1 complete water molecule, there are 2 H's. Last step, to go to grams, is 1.01 grams of hydrogen. And so that tells me I have 0.0343 grams of H. Okay, so then to get my oxygen, I have to go back to my total. So if my total was 0.255 grams, if I subtract out the carbon, and then I subtract out the hydrogen, I am left with the oxygen. So this gives me 0.0677 grams of O. So now I have what would have been the beginning of those other empirical formula problems. I now know that I have 0.13 grams of carbon, 0.0343 grams of hydrogen, 0.0677 grams of oxygen. And again, to get that oxygen, this was my total. I took my total, subtracted out the carbon, subtracted out the hydrogen. There's no label there, that's the hydrogen. And then whatever was left is my oxygen. Okay, so I am going to clear this out, and then I'm going to start again with my grams of each. Okay, so I'm going to start with the grams, so I need to rewrite those grams on here because I ran out of room. So I came up with, from the previous slide, I had 0.153 grams of carbon. So this is my carbon. And then my hydrogen was 0.0343 grams. And then my oxygen was 0.0677 grams. Okay, now I'm back to just a straight empirical formula problem. So I'm going to convert this to moles, and I get 0.01274 moles of carbon. Hydrogen, 1 mole, 1.01 equals 0.03396 moles of H. My last one, 1 mole, 16 grams. Oxygen is 0.004231. Okay, now I'm going to divide by the smallest. So that's my oxygen, so 0.004231, that gives me 1. 0.004231, that gives me 8. 0.004231, that gives me 3. Okay, so again, nice whole numbers, don't have to multiply. So those are my subscripts. So my isopropyl alcohol empirical formula is C3H8